Hello everyone, and welcome back. In the previous video, we introduced a number of important concepts for the analysis of differential equations. And in particular, we did this by walking through one long example that analyzed a single differential equation, which we derived from physical laws that govern the motion of a falling object. Now, as we walked through that problem, we introduced important concepts like what is an initial value problem? What are the general and particular solutions to a differential equation? What is a slope or a direction field? And what is an equilibrium? Now, in this lecture, we're going to continue introducing important nomenclature and topics for the study of differential equations. And what the goal here is to put us all on the same page so that we can all be talking about exactly the same thing as we progress through this lecture series. So for example, later on in the lectures, I could say to you that this method we are going to use is applicable to first order linear ordinary differential equations. Now, if you don't know what a lot of those words mean yet, you will by the end of this video. And in particular, you will be able to conjure up in your mind what these types of equations look like just based on the description that I gave you there orally. Now, the first thing that we're going to do is talk about the different kinds of differential equations. In our case, we're going to talk about two different kinds of differential equations as we progress through this course. The first of which is known as ordinary differential equations. So this one is typically abbreviated to ODEs. Now, you've seen ODEs before because this was in the title of my previous video. So I gave it to you without telling you exactly what an ODE is. So let's define it. What is an ODE? Well, an ODE is a differential equation that has only one independent variable. Now, typically, that independent variable is often time. That's the one thing that's always moving independently of how we act, right? We always put functions in terms of their value at a time. Again, think back to the example from the previous video. We looked at the motion of the falling object, and its motion was the velocity, v, as a function of only one independent variable, time. Okay, so the implication here is that there's at least one more different type of differential equation. Now, what I want you to think about is what could this possibly be? And if we think back to our calculus education, we remember that we have derivatives for functions of a single variable. And we also have derivatives of functions that have, say, multiple inputs, say f of x and y. And in particular, we remember that the name of these derivatives are partial derivatives. So we can also have partial differential equations. And in this case, we refer to these things as PDEs, right? So DE is always going to be in there for differential equation, but now I've got a P representing that partial term. And these things are just characterized by the fact that derivatives come as partial derivatives. So more than one independent variable. And in this case, there are a number of examples, and in particular, things get much more complicated, as you probably know from calculus, once you start having functions of many variables. So a notable example here is the so-called heat equation. So in this case, u is a function of space and time, and we have that the time derivative is equal to the second order space derivative. So this is a very, very famous partial differential equation. Partial because it contains partial derivatives. And this thing describes the heat at both a point in space and a point in time inside of, say, a room or something like that, right? So the spatial component is one of the independent variables. It says where you are, at what point are you measuring the temperature. And then the temporal component, which is one of the other independent variables, asks when are you measuring this. And you notice that this is a little different than the previous case where we were just asking when, right? Here now we have a where and when. Okay, so these two examples right here are talking about the independent variable in a differential equation. We could do something similar if we talk about the dependent variable. And in particular, we can introduce the concept of a system of differential equations. And that is when you have two or more unknowns in your equation. And by unknowns, I mean dependent variables. Okay, so here the difference between ODEs and PDEs is in the number of independent variables, space and time, for example. In the case of a system, it is a difference in the number of dependent variables. So, for example, I could have this differential equation, dx dt, which is equal to x minus xy. And then I also have another independent variable, dy dt, which could be minus y plus xy. Now, we can start building up and we can start combining nomenclature, right? We see that there is only a single derivative in these equations. That means that they are ordinary differential equations. There's only one unknown, that is t, typically representing time. But now you can see that there are exactly two independent variables, x of t and y of t. That means that I've got a system of equations. Now, what is this actual equation that I threw up on the board? Well, it's just worth sort of looking at it for a second. This is a very famous kind of system of ordinary differential equations. It's called a Lotka-Volterra equation. So this goes back to people trying to model animal populations. In this case, X is representing the population of a prey species, and Y is modeling the population of a predator species. Now, we don't have to fully intuit everything that's happening here, but let's take a look at sort of what this thing is saying, right? This is one of the things that we're going to hopefully be able to do as we progress through this class. In this case, this linear term here, this x term, is telling us that the population of the prey will increase, because we have a positive here, if it is completely left alone, right? Rabbits will multiply if nobody is eating them. But what this negative term tells us is that the predator is consuming some of the prey. That's why we are losing, so that's what this minus term is. And the rate of predation depends on how many predators we have and how many prey we have. Then if we look at the second equation here, we can see that we have a minus in front of the number of predators. And that tells us that if they don't have anything to eat, they're going to die out. So if there is just predators out there, you say just wolves with nothing to feed on, then they're going to decrease. That's what this minus is representing. Then you can intuit that this plus right here means that the population will potentially go up once they start eating or feeding on the prey. Again, we see that interaction term, x times y. We saw it right here as well, except when the prey goes down, the predator goes up because it's consuming the prey. Okay, so we don't have to focus on that too much yet. What we can do is we can continue down the line here with our definitions, and we can ask ourselves, what does it mean to have an order of a differential equation? So this is also another word that I believe I have actually used without defining. So let's go ahead and define it. Well, the order of a differential equation? Well, this is, now I know that it's sort of circular here. I'm using order to define order, but this will make sense as I write it. This is the order of the highest derivative. Present in the differential equation. So the DE, right? We've seen PDE, we've seen ODE. I'm going to write DE to represent differential equation. Okay, let's think about some examples, right? We've encountered orders already. If you think back to the last video with the motion of the falling object, it only had one time derivative, right? It was dv dt is equal to 9.8 minus v over 5. Well, that means that the highest order of derivative that's being taken is 1. There's only a first derivative in there, and therefore that is a first order ordinary differential equation, right? So now we can sort of put these things together, and we can sound really smart when we talk about them. Or I could give you another example. I could give you y triple prime plus 2e to the t y double prime plus y times y prime, and let's say this is equal to t to the 4. Okay, let's analyze this, right? I'm using some compact notation. The implication in writing this is that y is a function of t. Now we can see that there is a third order derivative here, a third derivative, a second derivative, and a first derivative. That tells us that the order of this differential equation is 3. That is the highest derivative that is present in this thing. We can also see that this is an ordinary differential equation because there is only one independent variable, that is t. That is the implication by these prime symbols. And we can go even further. We can say this is not a system, right? Because there is only one dependent variable. I just called it y this time. Now, the idea of an order extends to partial differential equations as well, but in this case, now we have to talk about the order with respect to each of the independent variables. So if I look at my heat equation right here, I would say that it's first order in time, there's only one time derivative, and it's second order in space, or first order, or order 1 in t, order 2 in x. Now, we have a general way of writing these differential equations up to an arbitrary order. In general, we write an nth order differential equation, in our case ordinarily, in the following form. So we say generally, we're going to define a function f which might depend on the independent variable. So again, I'm just going to be talking about ordinary differential equations. And let's use u to denote the dependent variable. And so this function is going to be nth order. And so therefore, it has derivatives in u all the way up to the nth derivative. This thing is an nth order ODE. That's sort of how we write it, right? So imagine you just sort of take everything all over to one side. So all I would need to do is kick this t to the 4 over onto the left side here, and then I would get it written in this form. Basically, you put everything on one side, and there's some complicated mixture, so we just write some general f here. Now, we can keep going. We can keep going into another fundamental concept of how we talk about differential equations. And this is probably one of the most important concepts that will be encountered. And that is the concept of linear and nonlinear equations. So this ordinary differential equation, so again, if I'm writing an nth order ordinary differential equations, so an ODE is linear if this f right here, so f, capital F's, both of them, is a linear function. So it's a linear function of u prime, all the way up to u to the n. Okay, so that means that you can have an dependent variable in here. You can have all of its derivatives inside of this equation, inside of this general function f that describes my differential equation. But they can only appear linearly. That means the exponent on all of them has to be 1, and they can't be multiplied together. So let's take a look at this one that I have written right on my board. Okay, so let's identify first just like the nonlinear functions, right? So this piece is linear, it's okay. This thing is nonlinear, we'll come back to it. This is linear, there's no exponent. This is nonlinear, and this is nonlinear. Well, actually, that one and that one don't matter, right? Those are the parts that depend on the independent variable t. Nowhere in my definition do I require dependence on t to be linear. So those are okay. If that was just the case, then this thing would be linear. But here's the problem, right? The problem comes from the fact that I have an independent variable, say y, dependent variable y multiplied against its own derivative. This is a quadratic term, right? This is like an x times y term inside of a function of two variables, right? And so therefore, this thing is non-linear, right? So this is the way that we talk about these things. So we say, so otherwise, f is non-linear. Now, think back to your education in calculus. What do you know about linear and nonlinear equations? There's a word that probably comes to mind, and it is easy. Linear equations are typically much easier to work with. That also transfers over to ordinary differential equations as well. Nonlinear equations are particularly hard. They are how I make a living, studying actual nonlinear equations. So in this class, we're going to focus a lot on linear equations, but we will also encounter some techniques of how to solve certain nonlinear equations as well. Now, before we move on, we'll say if f is linear, so if f is linear, then we can write it. So again, there's a general form for how these things can go. I can write it as a0 of t times u. So some function of t, again, doesn't have to be linear. It could be 2e to the t. It could be t to the 4. It doesn't matter. The 0 subscript represents that I have 0 derivatives being taken here. And then u of t, a1 of t, u prime, plus, then I've got a2 of t, u double prime, a3 of t, u triple prime, all the way up until an of t times the nth derivative, and that's equal to 0. Now that form that I have for you written on the bottom is exactly what this f would look like if it was a linear function. Look at linear in u, linear in u prime. In between here, linear in all other derivatives, and then linear in the nth derivative. That is the general form of a linear nth order ordinary differential equation, right? So we're building up. We have all these building blocks, and we can make longer and longer descriptions that precisely define exactly what we're talking about. Now, nonlinear systems, they abound. They can look like this. They have all kinds of sticky and ugly characteristics. They really define a lot of the sort of crazier motions that we find in life, right? So the things like my predator-prey relation that I just showed you, there's a complex balance there, right? Not enough prey, well, then the predators are going to die out. But as the predators die out, the prey are going to be able to grow again. But as the prey grow, predators have more to eat, so they'll grow. But then they keep eating the prey, right? And you get this sort of oscillatory relationship where, you know, they're sort of always sort of out of balance with each other due to overconsumption or just not enough to eat. So you get these very, very complex motions, and in general, things are just not that easy to describe when we have a nonlinear system. All right, so the last definition that we're going to talk about is probably the one that you feel is kind of the silliest one that we have to spend time on. But that is a solution to a differential equation, right? So you're sitting watching this, maybe standing, and you're going to say to yourself, well, Jason, of course, a solution is just a function that I can take derivatives and put it in. Of course, that is exactly true, right? That's what a solution to a differential equation means. But we have to be very, very careful about the intervals that these things exist on, right? So we say a solution. So, and in this case, of our very, very general differential equation. Remember, I can write any nth order ordinary differential equation like this. And we're going to say it's a solution on the interval. Let's say alpha less than or equal to t less than or equal to some beta. So these could be positive or negative. I could make this just strictly less than. I could make this strictly greater than or strictly less than here if I wanted to as well. While this is a function phi such that st is such that, well, first of all, such that I can actually take derivatives of this thing. Remember, if it's going to be a solution of the differential equation, it has to have derivatives, right? That's the differential part of the differential equation. So first of all, these things have to exist and satisfy, well, of course, they have to satisfy the differential equation. And again, what does that mean? Well, if I take all those derivatives, I put them into the differential equation, and I look at this function, this big general function, capital F, evaluated all these derivative functions, all as a function of time. That's the only thing that I have control over, is changing the value of t here. If this thing is equal to 0 for every single alpha, or sorry, for every single t between alpha and beta. Okay, so it feels like it's overdone, but as we sort of walk through this class, we're going to see where this concept actually comes up, right? Because we are used to things like maybe a function is equal to sine of x that exists everywhere, or maybe we're used to something like 1 over x that exists everywhere but x equal to 0. But with differential equations, we have to be very, very careful. All right, so let's go back to the previous example from the last video. We had v of t is equal to, this was 49 minus, I called it d e to the minus t over 5. That was my solution. This is solves. Remember, it was v prime is 9.8 minus v over 5, right? That was the equation from the previous slide, or from the previous video. Well, in that case, I have no problems with any values of t here, right? This solution exists for all time. That means I can go forward in time as much as I want, and technically, I could go backward in time as much as I want. It's still a solution to this differential equation. That tells me that alpha and beta have to be, or can be, plus and minus infinity. But like I just said, you can get problems. You could find out that, say, y of t equal to 1 over t. So immediately, this thing doesn't exist at t equal to 0. This is a solution of, say, y prime equal to minus y squared. Nonlinear, ordinary differential equation, not a system. 1 over t is the solution to this thing, right? But we remember that we also come with an initial condition. And that initial condition is going to tell us which branch of this function we are on. Remember, the function 1 over t, it has sort of two continuous branches, right? So this is y is equal to 1 over t here. So if I give you a point, say I say y of 1 is equal to whatever, 1 or something like that, that's going to pin down this point right here, and it's going to pin you onto this branch of the differential equation, right? You don't get to go all the way to infinity and come back around like it's Pac-Man and go back through into the negative values of t. So this thing is a solution of the differential equation, and that's only going to work for either this branch, the left branch, or this, right? So it's not the same as the domain of the function, because we remember from initial value problems, you have to pin me down with a point on the curve so that I can find a particular solution to the differential equation. In this case, that pinning down is going to tell me what my interval of existence is for this differential equation. Okay, so in this lecture, we went over a number of different ways to talk and classify about differential equations. In what follows, we're actually going to now walk through solving some of these differential equations. And in particular, I'm going to use a lot of the classification and the nomenclature that we introduced in this lecture. So, for example, the next lecture is going to go into integrating factors, which is for first order linear differential equations. I'll see you then.